Young biologists, this video introduces some things that are likely new to you, but still core skills that we'll use throughout the entire year. This is video 1.3, Standard Error and Error Bars. The video introduces these course topics to get enough info and hit the ground running for a bunch of class practice. Pause for a closer look. I'll start with standard deviation. Calculate standard deviation using the formula in the box. Remember, this formula is given on a formula sheet on the AP test and every assessment in our class. Standard deviation acts as an indicator of how spread out data points are in a dataset compared to the mean. A low standard deviation indicates that the data points aren't spread out all over, but are mostly clustered around the mean. Another way to say this is that a low standard deviation indicates that the mean is a good single number to represent the whole dataset when comparing to other datasets. Let's break down the aspects of this formula so it's a good tool for us. The S in here stands for standard deviation. The sigma tells us that we'll have to find the sum of some stuff that we'll get to later. X to the I is for individual data points. X bar, as we know, is for the mean. And N on here is the sample size or number of data points. Now, let's use this formula. I like to calculate standard deviation with the formula, but by making a type of organizer. Let's check it out. So here's my little organizer data table that helps me decrease mistakes. First, write each of these individual data points under X sub I. Then we put the mean as here, X bar, we put the mean right here. Now, I could put 59.6 because that's the mean, but in AP Bio, I'm going to say that rounding to the nearest whole number is okay. So I'm just going to put 60. 59.6 rounds to 60. Next, subtract the mean from each data point. So 68 minus 60 is 8, 79 minus 60 is 19, and so on. Next, we want to square each of those differences. So 8 squared is 64, 19 squared is 361, and so on down the line. To finish the numerator of the formula, we have to sum all of these numbers right here. So with a sum of all of these numbers adding up to 3022, we've done the whole numerator part. Then looking at the formula, the denominator is to divide this by n minus 1. In this case, n, the sample size, is 5 data points. So 5 minus 1 is 4. And then 3022 divided by 4 is 755.5. One more step. The formula tells us that we have to take the square root. So the square root of 755.5 is 27.5, giving us the standard deviation of our data set as 27.5. My challenge to you is to try this for the other data set. So you can pause the video when you're ready, and then when you're ready, restart to see the answer. So if you're going to do this, pause the video now. All right, hopefully you did all of those steps and you came up with a standard deviation of 10.4. If you got something wrong on that, check against the work that's shown here. So what does this tell us? Well, if the mean is one number to represent the entire data set, the standard deviation tells us how good of a representation that mean is. The variables quiz scores has this a mean of 59.6% and a standard deviation of 27.5. The stats quiz scores has a mean of 78.75% and a standard deviation of 10.4. This tells us that the stats quiz scores tended to be clustered closer to the mean, and the variables quiz scores were more spread out. The stats quiz scores mean better represents that data set compared to the variables quiz score mean representing this data set. And you can see why. In the variables quiz scores, this data point right here of 12% really messes things up. The mean gets lower to try and represent this 12%, but then that makes the mean represent these other data points not as well. In other words, outlier data points really impact the mean and standard deviation. Our next statistic is standard error, or standard error of the mean. And the good news is that the standard error works a lot like standard deviation. In fact, I took all of this text and just copied it from the standard deviation slide. So just like the standard deviation, the standard error indicates how spread out the data points are compared to the mean. And in the end, A small standard error of the mean shows that most of the data points are close to the mean, making the mean a good single number to represent the whole data set. And here's the formula from the formula sheet. Let's break down the formula from the formula sheet. Weirdly, it looks like it says sex, and although knowing statistics is sexy, that's not what this is. SE is for standard error, and the X bar is for mean, so standard error of the mean. S stands for standard deviation, just like in the last stat. And then N stands for the number of data points or sample size. So once you have standard deviation, standard error is pretty easy. Let's check it out. We'll check out the variables quiz score data set first. Here's our formula. So just divide the standard deviation by the square root of the sample size. Remember, there were 5 data points. So divide 27.5 by the square root of 5. And that gives an SEM, standard error of the mean, of 12.3. If you want to try for the second data set, pause the video right now. The SEM for the stats quiz is 5.2. All right, now what? So how does standard error even help us? Well, let's simplify what we're looking at. Here's just the means and the standard errors. If you compare the standard errors to the means, you'll see that the variables quiz had a pretty large standard error. So we need to be cautious about using this 59.6% as a single number to make conclusions, because that number doesn't represent too well what's happening in the whole data set. On the other hand, 78.75% is a pretty good representative one number for stats quiz scores because the standard error is relatively small. A standard error can be visually represented in graphs with error bars, like the examples here. Think of the error bar as being kind of like a confidence range for the mean, like plus or minus this amount. For example, in female fish, the mean length was about 20 millimeters. If you used a different sample size or a sample of female fish, the mean wouldn't be exactly 20, but these error bars tell us that we think it would probably be between about 18 and 22, the top and bottom of the standard error bars. And on graphs, these error bars give information to help us understand if differences between data sets are statistically significant differences. Look at this one again. Male versus female fish. Male fish have a mean length of 10 millimeters, and female fish have a mean length of 20 millimeters. From the error bars, we can see that the length of individual fish weren't spread out too much from the mean. And what we can say is that since these error bars don't overlap, the top of this one doesn't overlap with the bottom of the other, that means that this difference in length between male and female fish is statistically significant. Now let's check out this graph. The percent of pertussis is about 10% in this 1 to 3 year group, and about 15% in this 5 to 7 year group. It would be tempting to say that this 5 to 7 year group has way more pertussis than the 1 to 3 group, but check the error bars. The standard error bars tells us that the data points are kind of spread out all over the place for both this group and this group. So although there is more pertussis in the 5 to 7 year group compared to the 1 to 3 group, judging by these dots, the difference is not statistically significant since these error bars overlap with each other. All right, that was a lot. So let's take it back to the basics with our example. This graph summarizes our quiz example data, and let's add error bars. For the variables quiz, the standard error is 12.3, and for the stats quiz, the SEM is 5.2. To make error bars, you kind of make a big old capital letter I on both of these. The top of the I is plus 1 standard error of the mean from the mean, and the bottom of the I is minus 1 standard error. Having standard error bars helps give you confidence in your conclusion. For this graph, you can say that students did better on the stats quiz compared to the variables quiz. But then by adding error bars and see that these error bars don't overlap, you can say that the difference in performance between these scores is increased, and that increase is statistically significant. So let's recap. We learned about standard deviation and standard error, 2 stats that can show how spread out or tightly clustered data points are. Low standard deviation and SEM values tell us that data points are tightly clustered around the mean and that the mean is a good representative one number for the whole data set. High standard deviation and SEM indicates that there are some outlier data points or that the data points are kind of scattered all over and really spread out. Thus, any conclusions made by comparing means should be done with some caution. Visually, standard deviation and standard error of the mean can be turned into error bars on graphs. And this way, if error bars overlap, it tells you that a difference between two data sets is not statistically significant.